we're going to ignore all the numbers. I'm going to ignore this equation right here. Slowly erase the numbers. Because you can cheat a little bit if you have the numbers. Got it. All right. So, yeah, but we'll pretend it's not there. And we can color in like it never happened. Perfect. So this is the graph of f, the function f of x. Now we've done some of these already. If you have the graph of f, can you graph the graph of f prime? We're going to do that graph in green. And then we're going to have the graph of f double prime. We'll do that in purple. So the idea here is, even though you can't take the derivative and figure it out, can you get a sense of what's going on and then be able to graph the corresponding graphs that would go with that? Okay? You might be able to recognize this is an x squared graph. Okay? From that x squared graph, we're going to be able to have some of our ideas in our head of what happens when we do the derivative of that and what happens when we do the second derivative. Although you wouldn't necessarily be able to guarantee that it's an x squared graph, it might be an x to the 4 graph or something like that. But going to our green graph first, if we were going to graph the derivative, okay, there's some things that we would know about the derivative. If we were working through this process, the first thing we would find out is at this point right here, our tangent would be flat. So what that would show up on our first derivative test is we would have a point right there where we would know that f prime of x is equal to 0. I can't put a value there because I don't know what x is because we've erased all those things. But we know that f prime of x is equal to 0 there. So if I'm graphing f prime of x, I know that it's equal to 0 there. My original graph is already graphed. My original function is already graphed. There we go. Not my original graph is already functioned. Good. And you can see that it's going up and then going down. The only way that it's going up, we would know this part has to be positive, right? And this part has to be negative. So as far as our graph goes, we know that our function has to be positive. Our derivative graph has to be positive before this value and negative after that value. Now, if you make the assumption that this looks like an x squared graph, because we don't have the equation, it's not a bad assumption to make. But if you make that assumption and you choose, if you want to be accurate, you choose one point. Let's choose this point here, and let's draw the slope. Let's draw the tangent to it. If I count down 2 over 1, I might say that the slope there is -2. That's just an estimate. But if I say that the slope at this point here is -2, that means that -2 would be on my graph. And if I assume that's an x squared graph, that makes my derivative graph a straight line, which would look like that. I'll just temporarily draw, if it was an x to the 4 graph, then the derivative of an x to the 4 graph would be an x cubed graph. And what that would look like is it would be very similar to our straight line graph and would look something like that. So there we have our graph of f prime, based on the idea of what we know about graphing normally. Our original graph was going up before and down afterwards. Okay? To graph your second derivative, the strategy that I would use is take your green graph, your derivative graph, and do the same thing for your purple graph. So now if I look at my green graph, can you see that there are no maximums and no minimums? Okay? So there's no place along here f double prime of x would never equal 0. And here I'm thinking of f double prime based on the green graph. So I'm thinking of, if we would label our green graph with a new function, call it g of x, does it make sense that the purple one is just g prime of x? Because we're just going one derivative down. So I'm not going to be thinking about too much about concavity here. Okay? I can a little bit, but I'm looking at this just directly. From this straight line, if I use that one, it has no maximums, no minimums, no inflection points. In fact, if it is a straight line, it's always equal. The tangents are always equal because they're exactly what this slope is. And in this case, it looks like all my slopes, which we counted to be at negative, if we go over 1 down 2, all my slopes appear to be at negative 2. So when I draw my f double prime, it'll be constant at negative 2, which would make sense if we had a graph that's a line, then the derivative of a line is whatever the slope is, and then it's a constant function, which would be flat. So that's how we can take an original graph and then move through them. Yes?